session. We have 3 talks in the session, and the first talk is given by Mario patch-based methods for denoising, deblurring, and beyond.
Thank you. Okay, I'd like to begin by thanking the organizers for the invitation and for organizing this nice workshop. So I'll be talking about patch-based denoising, deblurring, and a few other problems. And sort of the motivating theme beneath it is this idea of dividing and conquer, that when you have a difficult problem, you should try to divide it into simpler pieces. And this theme will appear a lot. And you may have noticed that I've corrected the title of the workshop. It has a typo. There's this little comma missing there, which is called the Oxford comma. And so I wondered if it's missing on purpose because we are in Cambridge. So it should have a comma there. So divide and conquer it's a very old idea. I think it's attributed to Sumerians, but the first explicit instance is by Julius Caesar. And of course, modern politicians know about it a lot, and they exploit it a lot. They exploit it as a strategy. And there's even a beer called Divide and Conquer. So I think it should be a good thing to use in your work. Okay, more seriously now. So the outline is this is a brief outline. So I'll talk about patch-based image denoising. So this talk would have been very naturally presented right after Julie Delon's and Mila's talk because it starts at the same point. So how to do patch-based image denoising using Gaussian mixtures. Then I will talk about class-adapted restoration. So I will try to explore the idea that we should adapt to the classes of images that we're dealing with, rather than try to come up with general-purpose regularizers. So more in detail, I'll talk about this application to hyperspectral fusion or hyperspectral super resolution, to blind deblurring, and then I'll do some final remarks. So this is not a very mathematical talk. It's kind of a signal processing type talk. So I hope it's clear. So image denoising is probably the oldest problem in image processing. It goes back at least to the 60s. And of course the goal, you all know this, so it's given some noisy version of a known image, try to estimate this image. It has been asked if it was a dead problem. It is not. So if you look at how many papers per year cite the seminal non-local means paper, it's still growing, though now this year it's almost at 600 now. So it's not a dead problem at all. So it's important to keep on studying. If any doubt persisted, it's important to keep on studying image denoising. So the first instance of this divide and conquer idea would be that it's admittedly too difficult to write down a global model for images. So what these patch-based methods do is divide the image in pieces and model these little pieces called patches. And so the standard, the original, the first few methods that, still some do work like that, use this patch-based idea. And what they do is they start by taking the noisy image, they decompose it into overlapping patches. I don't know why this is so slow. They denoise the patches, and then they reassemble the estimated image by putting these patches back in their locations. And since the patches overlap, you have more than one estimate of each pixel, and so you average. And I'll talk a little bit more about how this averaging could be done. So there are many ways. So Julie mentioned many references yesterday, and Mila too. There are many ways to do patch denoising. So probably the first stream of methods used sparse coding on a learned dictionary. So this is work by Miki Alad and people who followed. KSVD is a famous instance of this approach, where you learn a dictionary that represents well the image patches, and then you say that noiseless patches should have a sparse representation on these dictionaries. You can do MAP or minimum mean squared error estimation using different methods. For example, using Gaussian mixtures. This goes back to the expected patch likelihood method of Zoran and Weiss. But there are other instances of these, like the one we heard about yesterday. And probably the earliest of all these kinds of work was by Boades et al., the non-local means paper, which essentially exploits the idea that typical image will be self-similar in the sense that there are patches that repeat. So there are typical structures that appear in many different places in the image, and this has been exploited also by lots of people. So this is a very small sampling of papers in these topics. There are hundreds of papers that do patch-based approaches. So the main question that you should start by asking is, and we've seen yesterday an instance of this question, is how to optimally denoise each patch. okay, which I'll next, for a few slides, I'll just represent it as X, just some generic patch. So on the Gaussian noise, you have the standard additive Gaussian noise model, so assuming that you know the variance. From this you can write a posterior density, so for the unknown patch given the observation, standard stuff. And then if you want to minimize the mean squared error, you know this is classical Bayesian decision theory, you should look for the posterior expectation of the unknown patch given the observed noisy patch, which amounts to computing this integral in the space of patches under this posterior density. Why is this so slow? Well, so the main questions here, of course, are how to choose or learn a prior that you can plug in there to compute this posterior, and how to compute this expectation. Okay, so these are the two questions that we need to address. So we need to compute, we need the prior, we know the likelihood. Of course, we need to be able to compute this normalization and to be able to compute this expectation. So essentially, there are three classes of approaches to answer these questions. So these fully non-parametric approaches, they make no assumptions about the form of this density P of X, of the prior. It just extracts patches and averages them in a certain way. So it's a fully non-parametric approach, and there are many variants and many descendants of this method and several different explanations for how they work. You can do importance sampling, and this is very recent work that we've been doing. You can do semi-parametric methods where you can assume that this prior is well represented by a mixture of Gaussians, for example, but other mixtures have been tried. And you can do fully non-parametric. I would argue that this non-local Bayesian method of Lebrun that Mila talked about yesterday is a fully parametric method, because when you're denoising a given patch, you find a group of similar patches and you learn a model for this group, which is fully parametric because it's just one Gaussian with one mean and one covariance. Of course, there are several variants of this. Okay, so a classical result in linear estimation that everybody knows about and it was mentioned yesterday is that if you know your prior, if you know the density, then the posterior expectation can be computed in closed form very easily using this expression which appeared in Julie's talk yesterday. And so the basic idea that underlies, for example, Lebrun's talk, the non-local Bayes method, is to, and Mila's talk yesterday, that you should estimate mu and the covariance, and then plug it in there to get these estimates. And you can do this, you can estimate this mu and you see either from clean or from noisy patches, depending on how you're doing it. Well, the problem with this, of course, is that image patches in general are not well modeled by one Gaussian. It would be a strange thing if they were. And so you need to divide and conquer again, so you need to divide the problem into different easier pieces. And one way you can do this is by, like is done in the non-local Bayes method, is to use only patches that are similar enough to the patch being denoised. So it was explained very well yesterday by Mila how this is done. So you find a group of patches that is similar enough to the patch that you're denoising, you group them, you estimate its mean and covariance, and you use that to denoise it. Or you can use a Gaussian mixture model. Okay, a Gaussian mixture model is sort of the idea that you can use different Gaussians to represent different parts of the configuration space of the patches, and rather than hoping that one single Gaussian will do the job. And so you can do these you can use this Gaussian mixture model, which can be learned either from an external set of clean patches, which was the original approach by Zoran and Weiss in the EPLL approach, or you can actually estimate the Gaussian mixture model from the noisy patches, from the noisy image that you are denoising. So you're adapting to this specific image. Or you can do things in between. So you can actually estimate a mixture from an external set of clean patches, and then also including the estimate sum of the noisy patches to adapt the model to your own image that you're trying to process. Okay. So this previous result, of course, is very well known that it extends to Gaussian mixture. So if you have a Gaussian mixture rather than a Gaussian in the prior, the posterior expectation still has a very simple closed form solution. It's a convex combination of estimates that were given if you had each of these Gaussians. So these betas, after normalization, are simply the posterior probability of component m given y. So it's how likely it is that this noisy patch was generated by the mth component of the mixture. And then you need to normalize it so that they are probabilities. And, come on. Oops. And these V, like I just said, these V sub m's are just the estimates corresponding to each of these Gaussian priors. And one interesting thing is that if you wanted to look for the map estimate rather than the posterior expectation, this would not be so easy to do. It's much more difficult than this, because the mode of a mixture of Gaussians is not the mode of the most probable component. There is interaction between modes, and it's just finding the mode of a mixture of Gaussians requires an iterative algorithm. That's not easy. That's not simple. Although sometimes it's not very far, but it's not. Strictly speaking, it's not. And another important thing is that you can still, using this model, you can still estimate the posterior covariance of your estimates, and you can get the diagonal of this posterior covariance in closed form. And so you know you have a measure of how confident how much confidence you have in each estimate of each pixel in the patch. And if you use that as actually its inverse as a weight when you reassemble the images from the patches, you're doing sort of the optimal aggregation in this sense, because you're weighting your estimates according to their inverse posterior variance, which is the optimal weight in the Bayesian sense. Okay, so lots of advantages from using these Gaussian mixtures. So how do you learn the Gaussian mixture? So this is probably a problem that goes back like 40 years. So you can learn it from a set of clean images, which is trivial because you just have a bunch of samples from a Gaussian mixture. You run EM, you have many samples, hundreds of thousands or millions. You just run it, wait. In the end, you have a mixture model which you can use, or you can learn it directly from the noisy patches. So the noisy patches, since I'm assuming that you know the noise variance, although this condition can be relaxed, you know that the covariance of the noisy patches is the covariances of the mixture plus sigma 2 identity, but you have to solve this maximum likelihood estimation problem under the constraint that the covariances are positive semi-definite. And so what you get is a very simple, very trivial change to the standard EM, where you see in the EM step where you estimate the covariances, you subtract, the Miller talked about this, you subtract the sigma 2 identity, you do it in the SVD domain, so these algorithms are more efficiently written if you do it in the SVD domain. And then you have to subtract sigma 2 and threshold at 0, so that you guarantee that these covariance estimates are positive semi-definite. Okay, so this has several interesting or relevant properties that I would like to mention. If this moves, does it move? Yeah, it moves. So one of the things is that we may include, and this sort of works reasonably well, if you add other constraints to these covariance matrices. For example, it's obvious that if you do unit stride patches, so the patches are extracted by moving your patch position pixel by pixel, any structure in the image will appear in all possible positions in the patches. And so this model is shift invariant. If you shift the whole image by a certain amount, your mixture that you estimate should be the same, which means that these covariances should have a tuplet structure. So you can add these constraints. So in the end, you end up not having that many free parameters in each covariance if you add these constraints. It's not a very over-parameterized model. Another important thing, and Julie mentioned this yesterday, sort of in a different perspective, was that by doing this thresholding, you're automatically selecting the rank of each covariance. So you're automatically regularizing, and so this is in a sense a generalization of this mixture of probabilistic PCA. Generalization in the sense that not all the components in the mixture have the same rank. So they live in different subspaces of different dimensions. So the only thing that you need to know is sigma 2. Okay. If you don't know sigma 2, you can estimate it in the EM algorithm, but you need to add some other model selection criteria. Okay. Of course, there's the issue of how to choose K. There's a lot of work on these. I've worked on these many years ago, and we have an algorithm that sort of works quite well and gives a very good estimate of K for this problem. But like Julie mentioned yesterday, the performance that you get in denoising using a Gaussian mixture model as a priori is not very sensitive to K. So K is not a big issue. Okay, so if you wanted to use this as a denoiser, well, if you just use it in this direct way, it gives you good results, but they're not up there with the state of the art. So you need a few other tricks, which are very well explained in this paper which has a title that I like a lot. It's Secrets of Image Denoising Cuisine, so there's a lot of secret sauces in there. So the main ones are that you should treat flat patches separately. This was mentioned yesterday. Another thing that usually helps that you should treat DC separately, so you should extract the DC component from the patch, keep it, don't do anything with it, you process everything else, and then you add DC back. You should repeat, so Mil also mentioned this yesterday, you run the algorithm twice. All of these improve a little bit the performance, although not by much, but it's sufficient, it's necessary to compete with state-of-the-art results. So this is work that my student Afonso did like 3 years ago. And at the time, what we had was that we were able to compete, although not beat, at least not consistently, VM3D. Probably not, well, by sort of the same amount that non-local base beats VM3D. So it depends on the images. I would say that it's not necessarily better, but it's competitive with VM3D. Of course, it is much simpler in terms of concepts. It doesn't explore any kind of collaborative filtering or anything like that. Of course, it is computationally a little bit more expensive. We can easily extend it to in-painting, like I think Julie mentioned yesterday. As long as you're dealing with the inverse problems that have a diagonal matrix, a diagonal observation matrix, it's very easy. So if you want to do exactly this, like you have your observed image for an in-painting problem, and you want to estimate the mixture directly only from this observed image, every time you have a patch, the patch has missing observations. So you need a version of EM that is able to deal not only with the fact that it's a mixture, but with the fact that every sample has missing samples. Every vector, every patch has missing samples. And there's a version of EM for Gaussian mixture models that does exactly that. So it can be used. The only difference now is that when you need to compute the different Wiener filters for each component, now the form is different because you have this mask matrix. So each of these matrices is a diagonal matrix of ones and zeros, the same size as the size of the patch. So if the patch is say 10 by 10, this is a 100 by 100 diagonal matrix of ones and zeros. It's a mask, essentially. So this gives very good results. It's state-of-the-art results. Again, not beating the state-of-the-art, but same as other methods that were specifically designed to deal with in-painting problems. I will not show lots of tables for now. For example, in this 80% missing data, with a mixture learned from these data, okay, so there's no external information. This is another algorithm for in-painting. I don't remember what SOP stands for. And we saw that the SNR is very similar, but you see that mixtures were able to capture the texture on the grass a little better, and so on. But spend some time now discussing the details of the performance. Okay. So, how can we use these for more general problems? So denoising is nice. There's a lot of people like trying to improve denoising methods by another 0.2 or 0.3 dB, but it's more interesting, of course, to use these for more general problems, so like inverse problems. Whoops. What's happening? Okay. Maybe I'm too far from the computer. Okay. So the inverse problems that you all, of course, know and love, so they're written like that. So you have an observation AX plus some noise. This, of course, is a good approximate model for lots of things, deblurring, image reconstructions of all sorts, super resolution, and so on. And the standard variational approach that everybody talked about in this workshop and elsewhere is this variational formulation, where you try to, well, under Gaussian noise assumption, where you have a regularizer, hopefully convex, so that you can compute it. Now, Anders told us that we cannot hope to solve these with arbitrary precision. There's some problems, but okay. But still it moves. And so there's a whole zoo of algorithms to solve problems like this. But one common thing to all of them is that they all require computing the prox. So this is wrong. This should be this phi, not this capital Phi. So the prox of operator phi. So they all involve. They cannot solve this problem with any iterative algorithm without being able to compute the prox of the regularizer. So it's a necessary component of any of these algorithms. So clearly, the prox is a denoising operator. It solves this problem is exactly of this form when A equals identity, which would be a denoising problem. And so several people had this idea some years ago. So I think the first paper is by Venkata Krishnan and other people. which is called the plug-and-play approach. He said, okay, why don't we take one of these algorithms, or any of them, and replace the prox of the regularizer, which is a denoising operator, by some better, some more sophisticated state-of-the-art denoiser. Would it work? And what can you say about it? Okay. There are a few other strategies to do this. Another very recent one is one by Romano and Yaniv Romano and Miki Alad and Payman Muhlenfar, which do something different. They try, given some denoiser, try to define a regularizer that is explicitly written as a regularizer depending on the denoiser. I will not mention this more in detail now. Okay, so my algorithm of choice is usually ADMM, so I always try to solve a problem like this using ADMM for several reasons. And in ADMM, again, like in any of the other algorithms, you would need to compute this prox of the regularizer with some weight, okay? It happens that most of the state-of-the-art denoisers cannot be written as the prox, at least explicitly, as the prox of some convex regularizer. And so the idea behind this plug-and-play thing is that rather than forget about the convex regularizer, just use some black box denoiser, that's some code that does denoising. So hopefully a state-of-the-art one, like BM3D. This is the one that in local Bayesian BM3D were tried in the original PNP paper. You can actually use a deep neural network, of course. You can plug it into your algorithm. If you have a deep neural network that denoises, I'm not going to exploit this for now. Or you can use the thing that I've been talking about, so patch-based Gaussian mixture model, mean squared error estimator for the patches with the aggregation and so on. Okay, so the algorithm will look like this. You have a denoiser, okay, plugged in the place where the prox was. Of course, the denoiser must be able to take in the noise variance because you need to give it this parameter. And of course, if the denoiser was a prox, you would know that this algorithm is guaranteed to converge, prox of a convex function. This is a well-known result. So the question, of course, an obvious question is, would this still converge if you plug this denoiser in there? Okay, so there have been some attempts at answering this question. I'll talk about it more a little bit later. The results in terms of performance, they are competitive. So this is a standard benchmark example, the cameraman blurred, so on. So this is a very, very state-of-the-art method. So this is the IDD BM3D, which uses this mesh equilibrium between deblurring and denoising, and which is it's very hard to beat. And this is ADMM with plug and play with the GMM denoiser. Okay. So conclusion that we extract, I don't want you to look at numbers in detail, is that for natural images this is okay, but it's not better than IDD BM3D, and it doesn't do much better than instead of a Gaussian mixture model if you plugged BM3D itself as a denoiser in ADMM. So essentially you see the bold numbers are scattered all over the place. Sometimes they are here, sometimes they are down there. So it's not a clear answer to how this works. Okay, so if we want to beat the state of the art, of course, so I could argue that this is a cheap trick, but it's to divide and conquer again and to learn rather than try to hope to beat algorithms for any image. Is try to learn a class-adapted denoiser, and a denoiser that's adapted to a certain class of images, say faces or fingerprints, and that's what we did. So, and that's one good reason to use a GMM denoiser, because you can learn the denoiser from a class of images. So the idea is that you have a data set of, say, faces or text images. You learn a Gaussian mixture model for the patches, then you plug it into the GMM minimum squared error estimate, and there you go. You have a denoiser that does, or that you can plug into the deblurring algorithm and obtain results. So this is just an illustration for text images, for face images. This is the Algor data set. And here, when you do this, now you beat by a lot all the other methods, which is sort of cheating because your method is tailored to faces or tailored to text, whereas IDD BM3D is a general purpose method for any natural image. But you beat by a lot. It's like by 3 dBs or 2 dBs or like 7 dBs or 3 dBs, so it's a huge gain, okay? So I would argue that in practice, if you can, you should do this, right? If you know that you're denoising a text image, why use a general purpose denoiser? You should use a denoiser that was tailored for text images. So if you have more than one class, okay, you might argue, Well, in many problems I have more than one class, so you can still address them. For example, you can learn different collection of different Gaussian mixtures, one per class, say one for faces, one for text. If you want to, say, process document images that have text and, say, a picture of a person, and then you can segment. The simultaneously as you restore, you can segment. So you have a collection of mixtures, one for each class. You can do patch segmentation, patch classification simply by maximum likelihood, or you can add some spatial regularization using, say, a Markov random field. And so you denoise each patch under the selected class. So you have different denoisers. You're classifying the patches. You're denoising them with the optimal denoiser for that patch, and then you iterate, and you get the results. Okay. So there's a synergy between restoration and segmentation, because restoration, of course, improves the segmentation because you have less noise and a clearer image, and segmentation improves restoration because by knowing what is in that region of the image, you can use a targeted model to restore that part of the image. So this is my colleague José, at a short bio at the end of some paper. This is the blurred version. This is what you get when you just use some general purpose non-segmented, so this BM3D, and this is when you do this. So the results are, it's hard to tell if they're better or not, but there's a side product which is a segmentation. So gray means text, white means face, black means anything else. So we can simultaneously deblur and segment the image. And if you look at it again, now, again what you have is, again, the big, well, a somewhat significant performance gain by segmenting the image and using targeted denoisers at each position. Okay, what about convergence of these kinds of algorithms? So we cannot say a lot, but you can say a little bit, okay, using a trick again. So if this denoiser was the prox of some convex function, then we know this converges with classical ADMM theory. And so we need to ask what conditions should this denoiser satisfy to be a prox. It will be a sufficient condition for convergence. So there's a classical result by Moreau which says that some mapping is a prox if and only if it satisfies two conditions. It must be non-expansive, and it must be the subgradient of some convex function. Okay. So if you can show that the denoiser satisfies these two conditions, this is enough and it's sufficient and necessary for it to be a prox. And if it's a prox, it's sufficient for convergence to happen. I'm not saying that only for proxies this would converge. There are probably weaker conditions, but this is the sufficient condition. Okay. So the question now is: does patch-based Gaussian mixture model MMSE denoising satisfy these conditions? Is it non-expansive? Is it a gradient of some convex function? The answer is no. It's not. It's very easy to show a simple counterexample. In a univariate example, so that I can do plots. So if you have a spike and slab type prior, where you have a prior which is a mixture of two Gaussians, both zero mean, small variance, large variance, so large variance, small variance. Very classical, used to be very used in machine learning and wavelets some time ago. You can write the MMSE in closed form. It's just this convex combination of these two linear functions, but the weights themselves depend on y, and so if you plot the MMSE denoiser, it's clearly not non-expansive. There are regions where the derivative is larger than 1, so it's not a non-expansive operation. So it would be a non-expansive operator if you had fixed weights, if you don't allow the weights to depend on y. So if you fix the weights, say beta 1, beta 2, then it's very easy to show that this is just a straight line. Okay, so with slope less than 1, because it's just a convex combination of two constants that are less than 1. So this would be. So the question is: are you allowed to freeze the weights? So well, for these algorithms, there's always this cheap way of guaranteeing convergence when the standard proofs for convergence require that some parameters are fixed, like for ADMM, for example. You say, okay, I'll let them float, and then after a certain number of iterations, I'll freeze them. And then, so from then on, I can guarantee convergence. So this is what we do in this case, okay? So we freeze the weights. So from this point on, I'll denote like beta IM is just the weight of component M at ith patch. And so the estimate for each patch looks like this. So it's like we saw it before. For a mixture, I've removed means, so I'm assuming that I'm using zero mean priors. It doesn't really matter. It doesn't affect any of these. I can write all these matrix, this convex combination of matrices in this way. So I'll call it Fi. It depends, of course, it depends on the noise variance. And then we introduce, which is something which is common in patch-based methods, which is a matrix Pi, which extracts the ith patch. So this matrix Pi is a matrix that has as many rows as the size of the patch, as many columns as the size of the whole image. It's a binary matrix that extracts the ith patch and gives it to you. So this xi hat, so the estimate of the ith patch, is simply obtained by taking the noisy image, extracting the ith patch, and multiplying it by this matrix. Okay. So how do you assemble? Of course, I'm assuming that the weights are normalized just to keep the notation simpler. I'd have to divide this by the sum of the weights. So how do you assemble the whole image? Okay, so to assemble the whole image, essentially you have to do this. So you have to extract each patch, that's Pi times y. You have to process it with the local matrix that was up there, and then you have to put the patch back. So the patch is put back in place by the transpose of Pi. It takes the patch and puts it in its place. And then you average, because the sum is over all the patches. So you average all the patches put back in their places, okay? And so I'll call this whole matrix here, so you see that the estimate is just a linear transformation. It's just W times Y, and W does not depend on Y, okay? So it's quite easy to show that this matrix has certain simple properties for any non-zero variance, which is it's symmetric, it's positive semi-definite, and its spectral radius is strictly less than 1. With some, it's quite just trivial, almost trivial. Okay, so we can write the denoiser as a linear transformation if the weights are frozen. Okay, so if recalling Moreau's corollary, now this is trivial because it is symmetric, it's non-expansive, of course, and it is the gradient of a function. It's actually this quadratic function, and so it is a prox. So with frozen weights, the GMM-based denoiser is a prox, and so you can guarantee that this PNP ADMM converges. Okay. So we might argue that this idea of freezing the weights is a bit like well, it's a cheap trick in this case, but in the next application, it's sort of extremely natural and actually something that you should do. So the next application is a bit more involved. I'm sure that some of you are familiar with hyperspectral images. I don't know how many of you would be. So the problem that I'm addressing is something called hyperspectral fusion. And it goes like this. So you have two hyperspectral cubes. So one of them has high spatial resolution, which is represented by this sharp image, but low spectral resolution. So you don't have many bands. Okay. And another cube which has low spatial resolution, sort of blurred, but it has high spectral resolution. Okay. There is a well-known trade-off, which is imposed by the physics of acquisition of hyperspectral data, that you have to trade off spatial resolution by spectral resolution. And of course, the goal in fusion is to combine these two to obtain one which has both high spatial and spectral resolution. It's called the hyperspectral fusion problem. Okay. An extreme case of these is pan-sharpening, where you have a panchromatic image of high spatial resolution, a color image or multispectral image of lower spatial resolution, and you want to combine the two to obtain a high spatial and spectral resolution image. And this is actually used in several cameras of phones these days, where you have actually two cameras, where one is a monochromatic camera of high spatial resolution, and the other is a color camera with a low resolution, and the final image is obtained by fusing the two. Okay, so this is just a simple instance of this. So how to write down this problem? Okay. So this can all be written using Kronecker products, but this is a more convenient way, because you can take your data and stack it, and as soon as you start stacking stuff, you get Kronecker products. But there's a simpler way of doing it. So Z is the fused image that you want to recover. It has LH, which is the same number of bands as a high resolution, as a hyperspectral image, and same number of pixels as the multispectral data. So reds are high, greens are low, or reds are big, greens are small, So you want to find an image that has high spectral and spatial resolution. It's called a fused image. Okay. So it's known that in hyperspectral images that these images typically live, so the spectra typically live in lower dimensional subspaces, not in the full dimensional subspace. So typically, so LH would be at the order of 100, so 200, 300, 400, something like this. Whereas P is like 10 or 20. Okay, you have a lower, much more lower dimensional subspace. Typically depend on how many different materials you have in the scene. Okay. So X are the coefficients of these that allow you to represent the image that you want to estimate on these subspace that contains the fused image. So now you basically attack this image from both sides. From the right, so imagine that the data are stacked in this way. So rows are frequencies, different bands. Columns are different pixels. If you multiply it from the right, you're blurring the image spatially. If you multiply it from the left, you're processing bands. Okay. So what this means is that all the bands are spatially blurred and then downsampled equally to obtain a low spatial resolution image. And here it means that all the pixels are spectrally processed in the same way by multiplying by this matrix R, which represent the spectral response of the multispectral sensors. And finally, you have noise. Okay. So if you assume that this noise is Gaussian, you can write a problem that you need to solve in that way. So you want to minimize these with respect to X, which are the coefficients of representation of your image Z in these bases that's in the columns of E. And to solve these, we use an instance of ADMM, which we call salsa. And, of course, that's the topic of the talk, instead of the prox of some regularizer, we use patch-based GMM denoisers. Okay. So the GMM, so now this is an interesting situation because we have a very high resolution image, spatial resolution. We're only processing spatially, so this regularizer only works on the spatial domain of each of the bands. And so we actually can learn it from an image of the same scene that's given to us by the multispectral image. And since the scene is the same, we're going to process the same scene using this mixture. We actually keep the weights. We assume that the optimal weights to represent a patch is the same for all the bands. Okay? So this is a situation where it's normal to do GMM-based denoising without letting the weights depend on the observations. So this is a case where you can easily, guaranteed that it will converge. So convergence is guaranteed. So you have this thing we call scene adaptation. So you have a prior that's adapted to the specific scene that you're processing. And since they are fixed, you can guarantee convergence of the algorithm because it is, although it doesn't look like it, you will see it is just a standard ADMM algorithm. So you can, to do that, you have to do this standard variable splitting and so on and so forth. I'm not going to spend a lot of time here. So you have to update your estimate X, which involves solving this very big quadratic problem. Then you have to update these auxiliary variables V1 and V2, which have to, again, purely quadratic problems. And then you have to denoise these. You have to update the steps for updating the dual variables, which I didn't include in there. And this is how the algorithm proceeds. Can you solve this? Well, one thing that's interesting to notice is that once you have fixed the weights of the Gaussian mixture model, your regularizer becomes quadratic. So the whole problem is quadratic. So you say, well, this is just a B quadratic problem, okay? Why don't you just solve it using something else? So IDMM essentially what it's doing is splitting this quadratic problem in a certain way that it becomes very convenient to solve each of these three steps. So let's look at them in more detail. So the first one, you need to solve this big quadratic problem with these terms, and it has a closed form solution, okay, which looks like that. You need to invert this matrix, B transpose plus 2 identity, and you can do it using FFTs. So this is, if you assume that you have periodic boundary conditions or unknown boundaries, which is sort of the same, you can do it using FFTs, and it's decoupled across bands. So this matrix, actually, you can pre-compute it once, you use it to process all the bands separately, and you don't need to recompute it anymore. So it's just a filter in the frequency domain. For the other two, for update of V1 and V2, again, you have to solve these problems. It's again a quadratic problem, so it has a linear solution. And the solution is again requires inverting a matrix. So now these matrices are very small because these are in the dimension of the subspace where the spectra live. So this is typically like a 10 by 10 or a 20 by 20 matrix, which you can invert once if rho is not changing and store, or even if you need to invert at each iteration, it's very cheap because it's a very small matrix. Okay. So this is small, this is cheap. So the algorithm sort of generic works like this. So you have the multispectral image, high spatial resolution. From these, by expectation maximization, you learn a GMM patch prior from these high spatial resolution images. And then this is the prior that you use in the denoising step. And so this is a loop of ADMM which takes both images, both stacks, solves the problem and produces the output. We can actually do a little better. Well, I could show you some results. It's very hard to show results for multispectral images because I cannot show you hyperspectral images. I can only show you the projections in RGB or something like that. So what we see here is that for a couple of classical scenes and different, this is synthetic data anyway, different experimental conditions. So this modified GMM method does better, or typically better than what used to be the state of the art, which is dictionary-based method. Not much better, but a little better. So you can do a little better. You can improve it a little better if rather than using only a spatial regularizer, you also use a spectral regularizer. A regularizer that, or a prior if you want, that knows how the spectra should look like. And you can do it also with the Gaussian mixture, and the algorithm becomes a little more. It has another part, so it has two denoising steps. It has a spectral denoising step, it has a spatial denoising step. Everything is decoupled, so the cost of the algorithm is essentially the same. And depending on how you extract the subspaces using SVDs or using some more sophisticated algorithm, you sometimes do a little better. It's not, well, on average, it's better. It's not always much better, but it's a very competitive algorithm. One thing that it opens the door to, which I'm not going to show, is that to do simultaneous hyperspectral fusion and segmentation of the image. Because if you learn different models for different types of materials, you can simultaneously do solve the two tasks. And so finally, I will, in 2 minutes, mention how this is used for blind deconvolution. I'll just show you, flash some examples. This sort of summarizes. If you want to do blind deconvolution using these types of methods, there are different approaches to blind deconvolution, but one of the classical ones is to solve this joint problem, where you're trying to estimate simultaneously the convolution kernel, the unknown image, and you have a regularizer for the image and a regularizer for the blur kernel. And of course, this is a non-convex problem, even if the regularizers are convex. So there's not, well, you can say a few things. So the standard algorithm to attack this kind of problems is proximal alternating minimization, which is what we're using. So you iterate between estimating the image given the blur estimate and vice versa with some proximal terms. And we use as image regularizer some class adapted plug and play priors. For the filter, we can either simply use like that it's positive and with maximum support, or if you're doing motion deblurring, you can say that it's sparse. I will probably skip this. And these are results that we've been obtaining. This is very recent results. So this is a blurred text image. What you see there is the blur, of course, and this is the estimate that we obtained, which is a little better. Well, I'd say 1 point something dB is better than if you plug BM3D. So this is with a GMM trained for text images. You can do it the same. Well, you can have, this would be very relevant because there's a lot of need to deblur fingerprint images. This is with a prior learned for fingerprint images. So again, it estimates the blur quite accurately and of course deblurs the image. You can do the same trick as before if you know that there's more than one class, like say faces and text. You could even segment the image and find where's the face, where's the text, and do the result. This is a very, all of these are state-of-the-art. This pan et al. is a state-of-the-art text deblurring method, CVPR 2014. In this case, we're actually using dictionaries, not mixtures. Of course, you can do it in color. There's nothing different there. You can just look at the results. And so some final remarks. So essentially I tried to argue that you should use divide and conquer strategies, and so in this case the 3 instances of divide and conquer were that patch-based methods are divide and conquer strategies. Using GMMs is a divide and conquer strategy because you have specialized models for different parts of your configuration space. And further, if you can do it, you should specialize to the image, the class of images that you're processing, rather than use a generic model. So the tool that we used was plug-and-play DMM, although other things could have been used. We were able to show convergence of the resulting algorithm under a condition, is freezing the weights. We applied it to blind deblurring, and ongoing work are in this direction. So trying to study the convergence of this blind deblurring alternating proximal method, addressing non-Gaussian noise, of course, would be important, and doing plug and play with other algorithms other than ADMM. ADMM seems to be extremely stable and accepts well this plugging of these strange denoiser in there. At least in our experience, it doesn't work so well with other algorithms. And that's it. Thank you. And since everybody's been doing these, we're also hiring people. We are hiring postdocs, not to work on image processing, but to work on machine learning. If anyone is interested, let me know.
I think we have time for some questions.
We have a nice view from the left.
So you went kind of quick at the end on the blind deconvolution. Can you tell me, maybe I missed it, what regularizers you were using, and in particular on the PSF?
Yeah. I know. Yeah, I rushed. So all in. Okay. So in all these examples that are that are motion blur like this, the regularizer for the PSF is sparsity. It's L1.
L1. Okay.
L1. So the regularizer for the image is the Gaussian mixture model adapted, blah, blah, blah. And the thing we use to solve, so we alternate between solving for the image and solving for the regularizer. Each of these is solved using ADMM, as before in the non-blind case.
And do you impose also bound or non-negativity constraints?
Yeah. Positivity
I see.
and support. Well, it should be and or sparsity. It's all 3. Yeah.
Thank you.
Can you say something about what you know about the convergence of this?
Of these?
Yeah.
Not much.
Empirically, have you observed that
No,
initial condition is important?
It is.
No.
It's delicate. It's not very robust. You need to initialize it with a pretty good. So in previous work with the postdoc I had, Mariana Almeida, we had a continuation method where basically you start with you add a continuation parameter where you start with a very strong regularization, okay, and then you slowly decrease the regularization, and that helps a lot to find a good solution. If you start with a very wrong estimate of the PSF, you're gone.
It can be proven that if you start with the wrong.
Sorry?
It can be proven that if you start with the bad initialization, you can go.
You can get stuck there. It's easy to show an example where it will stop right there.
Did you say how do you choose a number of components in the mixture model?
Yeah, well, in most of these experiments, we use some model selection method that I've written like 15 years ago, which does not require, well, it's specifically tailored for mixtures, in the sense that it's sort of a BIC type of method, like MDL or BIC, but BIC requires regularity of the model, in the sense that the variance of the, essentially under BIC or MDL, is the idea that the variance of the estimate of each parameter goes down with 1 over n, number of samples. But for a mixture model, that's not true, because you may have, it depends on how many points are sort of attached to each of the components. So you need to take that into account. And by taking that into account, you can write an EM algorithm that you can initialize with many components, and it will automatically delete some of them, and it converts to a good. So, but like I said in the beginning, it's not a very critical issue, and I think Julie also mentioned that yesterday. This always works sort of more or less the same if you use like 40 components, or 50, or 30. It doesn't change much.
Well, in the hyperspectral case, are you using a multivariate Gaussian?
Yeah.
So across all the spectral bands?
Yeah, but it's not the spectral bands. It's the lower dimension subspace. So it's like 10, dimension 10 or 20. It's not 200. So it's a small mixture. It's a small dimension mixture. So the covariance is like 10 by 10 or 20 by 20.
In one row behind you was first.
Just a quick question. Have you looked at diffusion of low resolution multispectral with high resolution?
Sorry? I can.
Low resolution hyperspectral with high resolution multispectral. Have you looked at fusing LiDAR data with hyperspectral data?
No. I haven't.
There was an IEEE contest
Okay.
a few years ago on that topic.
I haven't looked at it now.
Maybe one quick question.
So you have some objective function for which you have an ADMM strategy,
Yep.
and you replace the prox with some other algorithm. Are you monitoring the original objective, or you're just
No.
replacing the prox?
The original objective is gone. Actually, it turns out, like I think I mentioned it. It turns out that if you're using, you can go back. So if you say, okay, I'm going to replace the prox. I'm going to replace, well, let's do it here. I'm going to replace the prox by some denoiser. Okay? If this denoiser is the one that I said, a Gaussian mix, or a convex, let's call it a mixture, a convex combination of Gaussians, it turns out that these objectives, it's like if you had a quadratic function here. Where it's like if you had a Gaussian prior, where the covariance is that convex combination.
But only if you fix the weight.
Only if you fix the weight.
Okay, but all of the work is done before you fix the weights.
Yeah, no, in this case, I never unfreeze the weights. They are frozen from the beginning. Because I keep the same weights that I run EM on the high resolution image. Since the image is of the same scene, I will assume that their spatial behavior is the same. So I keep the weights. Of course, it was too fast.
That's right.
So if you see here, I estimate not only, so I estimate the covariance matrices and the weights, and I give the weights to the denoiser. The denoiser uses the same weights that came out of the last iteration of EM. I never touch the weights again. It's a strong assumption. We've made a lot of experiments to see if this was a good assumption, and it is a very good assumption actually. So the spatial structure of each patch has lots of commonalities across bands. It is because essentially have boundaries between objects and edges and stuff, and they're not always the same across all bands, but they're very highly correlated. There's very strong correlation across bands.
But does that mean you could have used any optimizer for this quadratic problem?
You could, yeah. I said that, yeah. You could, but this turns out to be extremely efficient because it splits the. Of course, if you try to write this down as just a big quadratic thing, the matrix that you get for the quadratic problem is complicated. It has a complicated structure. Yeah, you could, but you would not be exploiting the fact that you can invert BB transpose plus identity using FFTs, and so you would not exploit the decoupling of space versus bands. So you're exploiting the structure of these matrices.